Good morning, everybody. So, I am going to basically talk about another method which is of great importance to control designers for the development of control system, and that is system identification. Okay. So, quite often, and helicopter is a very good example of that we end up with extremely complicated systems which are very difficult to model mathematically. So, even if you use the best physics based model, you may not be able to replicate the dynamics of the system with that much of accuracy as you would want it to have. Okay. And you have seen, okay, I mean, we in the last 3 days actually we went through several things, and first 2 days actually you saw, I mean, what is the best we can do with the basically a helicopter model. But then, I mean, going beyond that actually is far more challenging. I mean, developing the flight dynamics model itself may take you years actually, if you want to really match the level of accuracy available through best state of the art codes. Okay. So, this method actually is a nice technique. Okay. So, this is the outline of my presentation. So, I will start with the introduction, then what we are doing is actually we are following an approach called frequency domain system identification. Now, you can also carry out time domain based system identification. Also, to do these, or rather to apply these methods, okay, you need not actually have to resort to some sophisticated software. I mean, some of the basic tools are available in your MATLAB itself. So, MATLAB has system identification toolbox which can be employed to identify I mean models in real time, okay, using mostly time domain based methods. Probably they have frequency domain based methods as well, okay, but I have not seen. So, what we are using actually is a frequency domain system identification. So, ideas are similar, okay, approach is slightly different. So, I will go in the details of this particular method, okay, which is what we are employing right now. So, then we will talk about, okay, how we go about conducting flight experiments and how do we collect data, because system identification is a approach where you actually have to give an input to the system and collect the output data and use the output data to somehow come up with, I mean, sort of correlate the input and output and try to fit a mathematical model around whatever you observe. So, this is a very important and key step, flight experiment and collection of data. Then development of model structure, I will talk about that. Initially, to check whether you are doing things correctly, it is nice to look at CISO models, single input single output kind of model identification. It is simple and gives you reasonable accuracy, and also it is nice for doing simple, okay, your cascaded loop based designs and so on, okay, simple control designs. And then MIMO model identification. We have so far carried out 2 types of identification. One is regular 6 degree of model identification, and then hybrid 8 degree of freedom model, okay, where we also include the blade flapping angles beta naught and beta 1c and beta 1s. Okay. So, I will talk about all these things. Okay. So, let us see, okay, what is first system identification. I briefly told you what sort of it is. It is essentially a data fitting process, and system identification employs experimental input output methodology. So, we collect some data based on known inputs. So, we measure or we exactly know what input we are giving to the system, and in that process we collect some data, and that is the output from the system. And finally, we want to produce some mathematical representation of the system dynamics. Okay. So, that is our goal. So, we start with some assumptions. We have a physics based model, okay, which you can use for simulation, and that gives you the motion. So, this is what we normally do in the flight dynamics modeling, okay, what we saw in the first couple of days. We have some assumptions, and very often for complicated systems we end up with lot of assumptions, and we carry out physics based model development, we do simulation and see what we get from the simulation. The system identification kind of works in reverse order. So, here we are starting with the model and then we get some motion. In this case, we actually measure first the aircraft motion data. So, it effectively tells you that you need to have the physical model itself, because you are going to give an input, you are going to actuate it, you are going to fly it and so on. So, we need to measure the aircraft motion first.
Can I put a question?
Yeah, sure, sure, free. Yeah.
So, how is system identification different from mathematical modeling of the same system?
So, mathematical modeling is what we are seeing here. So, here I mean you are actually developing physics based models, and you are trying to employ physics and knowledge of the system to develop a model which is just a mathematical representation of everything. Okay. It need not require you to actually have the physical model with you, in the sense I need not have to have a helicopter to develop my flight dynamics model. I would definitely need some geometric parameters, but beyond the parameters and some data, I mean I do not need actually require to fly the vehicle itself. In system identification, we start by flying the vehicle first, okay, because unless and until you have the vehicle, you cannot do a system identification. So, I like the small helicopter you saw earlier, okay, we take that helicopter, we fly it, we measure the response to given pilot input, and from that we try to extract the model. And there, I mean, you need not know the physics of the system also. So, there are two approaches in that also, we will talk about that in a moment, but it is not necessary for you to know the dynamics of the system. Okay. You can be completely blind about the dynamics and you can still identify models. So, effectively you are trying to sort of do some kind of curve fitting.
Just if you have the knowledge of the governing laws of the system, then we can start with that.
No, that also is not required actually, that is what I am saying. I need not know any governing law, anything actually about the helicopter, how helicopter is going to behave. Okay. I just take the helicopter, I instrument it. I should just have the knowledge of what I have to measure, okay, and I should know what kind of inputs goes into the system. So, I should know input and I should know some way of measuring the output. If these two things are available, then without knowing what actually this helicopter does, okay, how it is going to fly, you can still identify the model. Okay. So, it is something which is like you can think of this like a black box approach also, but it is not necessary that you have to follow that approach. There is another option also where I mean we can actually bring in some amount of physical realism. That is, we can bring in some equations and try to use the system ID to improve the identification of parameters in the equation, like the equation which we saw earlier, okay, the linearized flight dynamics model which we developed, which had all those control derivatives and your stability derivatives. We can actually use this approach to identify those parameters also, okay, and that is what we kind of we are trying to do right now. Okay. So, we start with measured aircraft motion, okay, then we put the motion data, the input and the output information through the system identification process, which we are going to learn about today, and from that we extract the model, okay, and from the model then we try to bring in the physical understanding. Okay. So, here I mean physical understanding is required a priori. You should have understanding, okay, how this actually aerodynamics is going to behave, how the rotor and the wake is going to interact, how is the induced velocity going to be there, all those information is required when we develop the flight dynamics model. On the other hand, none of those things are actually required when we do this in this particular way. So, this is the comparison between simulation versus system ID. Okay. So, what are the typical applications for system ID? One is validation and upgradation of simulation models. Okay. So, I already have a simulation model and we already have like developed some models which we have given to AD and we are using ourselves also. Now, how do we know that these models are actually good enough? Do they actually represent the physical system or not? So, it always this kind of identified information from flight tests help us validate and upgrade our simulation models. Okay. So, we can use the information from the system ID to improve our estimate of some parameters. For example, I mean bigger helicopters, sometimes you may not know the inertia properties of the helicopter. Even for a smaller helicopter, I mean no manufacturer will give you the inertia properties. So, you have to estimate those properties. So, you have to use various methods and so on, but sometimes I mean you can extract some of these informations which are not known that easily through system ID. Design and optimization of control systems is of course one of the key applications. Handling qualities, okay. So, how a helicopter handles, how it behaves, how a pilot would actually think about a helicopter, okay. Those parameters come in handling qualities. Okay. So, it is system ID is used quite extensively for this particular purpose also. Now, system identification is not just common to helicopter, okay. It is not like something which is specially meant for helicopters. I mean this particular approach is generic, you can use to identify any kind of model. Okay. You want to know the response of a car, okay. That if I give your pedal input, that is your accelerator input in car and how much speed I end up getting. So, there also you can give an input and look at the output and you will actually be able to identify the model. Okay. So, all those things are common to everything, but there are some specific challenges when you apply this system identification to helicopters, and those are here. One is that we have rotor on the helicopter which actually transfers significant amount of vibration to the fuselage of the helicopter, right. I mean when we are doing the helicopter aerodynamics, we discussed this, that any NB per rev, okay, and plus 1 and minus 1, because of the sine cosine addition, it gets transferred to the helicopter fuselage. So, in the fixed frame we always have, if the number of blades is 4, you will have 4 per rev, 8 per rev, 12 per rev, 16 per rev, all these harmonics are going to be present. So all these vibrations are getting transferred to the helicopter fuselage. Beyond that, there is always some imbalance. Yeah. So imbalance is rotating imbalance, that is the CG of the blade rotor system, it is not going to coincide with the CG of the, or sorry, the axis of rotation of the rotor. As a consequence, there is always this also 1 per rev vibration that also gets transferred to the fuselage. To understand this 1 per rev better, I believe all of you have used washing machine at some point of time. Yeah. When your clothes get actually collected on one side, you will see that the whole washing machine will start shaking like crazy. That is your rotating imbalance, because the CG is actually shifted to one side and you have a offsetted CG rotating at high speed. So there is centrifugal force which gets transferred or rather generated because of that, and that actually creates a lot of vibration. So all those vibrations are there, and as a consequence there is high level of measurement noise. So your signal to noise ratio actually diminishes significantly. And this also we have kind of highlighted earlier, that is there is significant amount of cross coupling. We discussed elaborately how one particular motion actually always results in the second motion. If my helicopter rotor pitches up, it will also try to roll to one side. So pitch and roll is tremendously coupled at all times. There is coupling in between even blade motions, flap and lag are coupled because of Coriolis acceleration and so on. So there is high degree of interaxis coupling, and the vehicle itself. So helicopter, we did not go into the stability aspect of the helicopter, that is if you do the, we did derive the equation, linearized equation. If we, and we also mentioned that if we do eigenvalue analysis of those A matrix which we got, linearized A matrix, I would actually know eigen values which will correspond to the frequency of helicopter, natural frequency of helicopter system. So if we had done that, you would have learned that helicopter, even though it is designed and made primarily for doing vertical takeoff and landing and hovering flight, it is actually highly unstable in hover. So a normal helicopter without any autopilot on board, either autopilot or rather some kind of stability augmentation system which we called SAS. So either this SAS could be either mechanical or it could be electronic. So without any kind of SAS, it is almost impossible to fly a helicopter. So this is another big challenge. So vehicle is unstable. So now if I want to develop a controller for a new helicopter, I am making a new helicopter and I want to develop an autopilot for that. So this vehicle to begin with is unstable. So how would I fly that actually? So vehicle is I cannot fly it actually, so I cannot do system ID. So I would need some other way to at least have some basic controller on board. Then only I can fly it, and then I can do a more comprehensive identification, and from that I can come up with a better control design. So these are the challenges. Now if you look at the literature, when people started actually doing the system identification business, the oldest paper available is actually from 1989, when this Kaletka tried this particular approach on BO-105 helicopter. So BO-105 is one of the very highly maneuverable helicopter made by European company, and so he first did this 6 degree of freedom identification. So he tried to identify a rigid body model. 6 degree means, I mean, you are only considering the rigid body motions, you are not concerned about other states of the helicopter. Then Tisler, who has been kind of pioneer in this area in US especially, he has developed this software called Cypher, which stands for Comprehensive Identification for Frequency Responses. This software actually is sold by NASA, and it is available for purchase by anybody, especially academic institutions. You get significant rebate also. So you can buy this software just for $200. Normally if you buy as an industry or something, it will cost you more than $1,000 or something, probably even more. So through academic license, I mean, it is very easy to procure. $200, just 10,000 rupees, 12,000 rupees, that is all. So we have even procured this, and we are using this because it is something which has been developed over, you can see, more than 2 decades, and it is quite extensive right now, and it can do up to 9 degrees of freedom. So in 1992 itself, he started developing this model, and he did this 9 degree of freedom hybrid model identification. Then Ham in 1993, he also tried something high bandwidth control, and rotor fuselage coupling effects, he said this should be accounted. Then Tisler further used his software to do system identification for many other vehicles also. So beyond normal helicopters, he could actually also do it for this experimental tilt rotor vehicle which was called XV-15, which was tested at NASA extensively, and this particular vehicle led to development of the current tilt rotor aircraft, which is V-22 Osprey, which is used quite a lot in Afghanistan war and many other places. So this particular approach was used to even identify this plant model for this very complicated aircraft, because this is a VTOL aircraft which takes off like a helicopter and then it becomes an airplane. So, you have to design controller. So, I mean in control system domain, people say that developing a autopilot for a vehicle like this is probably the most challenging thing, even more challenging than what is that for the helicopter. So, he applied all this for that. So, beyond bigger vehicles, Mettler in 2002, he has also a book on this topic. He developed a parameterized model for a Yamaha R50. Later on, this Yamaha R50 started being called as Yamaha RMAX. It was slightly upgraded version of this particular helicopter. Now, this particular helicopter has been actually, originally it was brought in the market for agricultural use. You can see this picture actually shows this bottle here for pesticide spraying. So, it was used extensively in Japan, US and even in Australia for spraying pesticides on your fields. But now this has been taken out of the market completely, and I believe Northrop Grumman has taken the rights to this helicopter and they have converted this into actually a military version called RBAT, Yamaha RBAT, or rather it is called now RBAT just, that is all. So, he applied this particular approach for identifying model for this. Then Cheng, he used on RMAX, which is slightly bigger than this one. He did this again 9 degree of freedom state space model development using this for both hover as well as forward flight. So, this method, what we are looking at, this frequency domain based approach is actually a linear method, because it frequency domain means it has to be periodic. Your response forcing everything has to be periodic. The moment it is periodic, that means it has to be linear actually. So, the way we normally do the identification for the entire flight envelope is that you classify or break your entire flight into different paradigms, and I will identify models for different stages. So, I will have a one model representing hover, I will have another model representing a speed of 0.1 advance ratio, then 0.2 advance ratio and so on, and then finally, I can stitch them using some interpolation scheme to have a nice smooth model for the entire flight envelope, because helicopter behaves in a particular way in hover, it will behave in a different way at say your 50 km/h speed, a different way at 100 km/h speed because of the aerodynamics and everything. So, we have to identify all these models separately. That is one challenge with this particular approach. Then my colleague Joe Conroy at Maryland, he also had applied some of these identification techniques for a really small, almost the kind of size which we had brought earlier, that category helicopter in 2011. So, right now our objective, whatever work we have done so far, I am just presenting one of my students' work here. So, our goal was first to identify this hybrid 8 degree of freedom model. We are not looking at the yaw dynamics, because yaw dynamics is very fast, and so we just kind of remove that part, otherwise all other states are almost there. So, this is a small helicopter, slightly bigger than the one which you saw. So, the one which you saw was actually 250 class helicopter. So, the distance between the main rotor and the tail rotor is around 250 mm. This one actually has 450 mm distance, slightly bigger. So, today when we go for demo in the afternoon, so our tutorial today actually will be in the helicopter lab. So, you will all get a chance to see all our helicopters and also get to see the flight of the helicopter there. So, there you will see whatever things which we have. So, vehicle will actually leave from here. So, all of you have to, I think before that there is a class. So, after that class vehicle will take all of you to helicopter lab. So, we are using Cypher, and this small helicopter we have instrumented, and now we are going to check. But this is actually just our intermediate step. This is our preliminary stage where we are trying to learn about this. In India nobody has been doing system identification for helicopters at all. So, we are first people who started learning about this, and we said we will try. So, we started with a small helicopter. Finally, then we will actually apply now probably in another few months time, probably this month, and by next month we will actually do extensive testing on this helicopter, our 10 kg helicopter, which you will see actually the demo of also today in the tutorial part. So, we will do very systematic and very broad parameter estimation and system identification for this helicopter. And our ultimate goal actually is to do it for 2.5 ton Chetak helicopter, which AD is actually working with, and we are actually helping out with this. So, they are in process of instrumenting helicopter, this Chetak helicopter, and then they will arrange for flight testing. They will give us the data, and then we will try to do the identification of the model based on our experience with this kind of work. So, what are the different elements? So, like I mentioned earlier, there are two paradigms or two different approaches which we can follow in the frequency domain system identification thing. One is non-parametric modeling, other is parametric modeling. So, the key difference is that in this non-parametric modeling approach, there is no need for knowing anything about the model, okay, like which what we were discussing earlier, that even if you are completely ignorant about the dynamics of the vehicle, okay, you can go with this particular approach. Other is parametric modeling, but then this may be slightly restrictive. Okay. You may not be able to match your model to wide range of frequency domains, because I mean you are limited to say mostly rigid degree of freedoms only. Okay. But in parametric modeling, what we do is that we use our knowledge of the system somewhat, okay, and try to improve our estimation of the parameters for our known model. So this would effectively you make use of some kind of simple flight dynamics model. Okay. So let us see how it is done. So there is no model structure, okay, is assumed a priori. Okay. It provides excellent insight into vehicle dynamics, and quite few applications are there, like piloting the loop simulation, stability margin determination, and tuning of physics based simulation models. Okay. So this can be used for all those things, okay, because we don't know much about that. Then for parametric modeling, okay, model order and structure has to be assumed. So we must understand that, okay, what kind of dynamics we are expecting from the vehicle. So we must define some structure for the model. Typically we go with state space description, and we make use of aerodynamic stability and control derivative representation. Okay. So whatever we derived, okay, earlier in the flight dynamics lectures, that linearized model of the overall system, we will have to make use of that, okay, and we will try to improve the identification of the parameters which are used in that. So this application of this particular approach is control system design and also for math model verification. Okay. Now this is overall flow chart. Okay. This is taken probably from the Cypher manual or something, okay, and it depicts how Cypher actually makes use of this approach to do the system identification. Okay. So starting point is that we take the aircraft, okay, and we give it frequency sweep inputs. So what is this frequency sweep inputs? So normally when a helicopter is flying, okay, I will show you actually a demo video also, okay, where we give this frequency sweep inputs. Normally, I mean, your helicopter is flying, you give some input to maintain the position. Now pilot will actually on purpose try to excite the motion in the helicopter. Okay. So he will give very fast inputs. Okay. So the rate at which he is changing the various input sticks, that is the cyclic stick and collective stick. Now of course for a small helicopter we don't have cyclic and collective physically. What we have is our remote control, which has actually your throttle and your side stick. So we will actually perturb these sticks in a very fast manner, which will excite the source plate and induce certain motions in the helicopter. So we want the helicopter to actually fly in a very fast and sort of aggressive manner. The idea is that by moving these arbitrary high frequency inputs or different frequency inputs, we excite different response from the helicopter. This idea is very similar to, I mean, you are measuring the frequency of a structure. So if I want to measure the frequency of a small beam, okay, what I do, I actually go and just gently tap the beam, and I will have some sensors on the beam which will actually tell me what frequency it is oscillating with. So the approach is very similar. So we are trying to give some disturbance to the helicopter, and I want to see how the helicopter is going to respond to those disturbances. But in that process, we have to ensure that we do not lose control of the helicopter. The disturbance would be not so large and so high that, I mean, helicopter starts behaving like crazy, okay, and crashes and so on. Okay. By the way, yesterday we actually had a crash and one of our helicopters got totaled. Okay. So it's an electric helicopter. I don't know why it has happened. I mean, this is second time one of our electric helicopters has gotten completely destroyed. The autopilot actually just turned off on its own, okay, because right now we use hobby grade autopilots, okay, and they don't have very good reliability. But I mean, luckily somehow our engine helicopters never had this problem. We had flown our engine helicopters for over 60, 70, 80 hours. Okay. But this brand new helicopter which we had flown probably only couple of times, okay, and just yesterday it was a pretty spectacular crash actually. Okay. I mean, it was pretty close to ground and it just flipped over. The autopilot just reset or something. The hardware actually got reset somehow. I don't know why. Okay. Anyway, so we'll keep you at a safe distance. Okay. Don't worry. Okay. When you go for the demo. So we give this input. Okay. I will show you what these inputs look like. Okay. Then we collect the data. Okay. And this data actually we have to check the consistency of the data. Okay. How consistent and how accurate this data is. So this consistency, and then we have to reconstruct some things. We carry out multivariable spectral analysis. Then from this conditioned okay, input and output data response, okay, whatever we have collected. We go for some partial coherence, we can also go for transfer function modeling for single input single output cases, or we go for frequency response identification. We make use of the frequency response identification criteria and use our identification algorithms to find sort of derive the model. Okay. So all these things will become more apparent when we go to the subsequent slides, because each of these are discussed in somewhat detail in that. So we will define some mathematical model, okay, and then we will try to fit things on that. But before that, we have to do this coherence check, okay, to ensure that the data which we have collected is of reasonable fidelity and we can trust it, it has good signal to noise ratio and all those things. So once the data goes to identification algorithm, okay, it will tell you the mathematical model and control derivatives and time delays. That is our goal. Once the model has been identified for multi-input multi-output system, now to identify this also you may have to actually specify some initial guess values, because this estimation or this identification actually happens in an iterative manner, right. So it is not like, it's not a magic, okay, it will automatically populate all the values. We have to start with a known model or sort of a known structure for the model, and then we have to give some guess for those numbers. So like all those parameters we saw, all the control derivatives and stability derivatives, we would have to give some guess value for that to start the whole process. This guess value actually can be obtained based on your existing flight dynamics model, or I mean we can use closed form formulas which are available in the book to start the process. Sometimes it may work for you, sometimes it may not work for you. Okay. When it does not work, then we have to do some better guess. Okay. We have to sort of improve our guess. And once you start using this particular tool or this particular approach for long enough, I mean then you would also know, okay, what kind of guesses are going to work for a particular scenario. Okay. So it improves with your experience. Now once the model is identified, okay, we typically, so when you perform so many flights, okay, you will use most of the data for your identification, but you will also keep some extra data, some extra flight test data which will not be used in the identification of the model. These extra flight cases are going to then be used for verification. So you can see here, okay, so the similar flight data which was not used for identification would be used for verification. Okay. And once you get reasonable match and you are satisfied with the correlation between the flight test and the identified model, then you can use it for all kinds of purposes. Okay. So what are the advantages of this particular approach? It is possible to individually specify frequency range used for the fitting of each input output pair. Okay. So we can give the range of frequencies which we want to fit over, and so there, I mean again we kind of need to know the kind of frequency response we expect from the system, because we are giving it some kind of excitation. If we have some knowledge of the model, then we can be wise in choosing our frequency range. Yeah, we know that, okay, my helicopter is going to respond in only 2 radians per second to say 10 radians per second. So I will put the frequency window in that range. Okay. I will not go and aim for like 100 radians per second and so on. So some knowledge is useful. Effectiveness in selection of frequency range, same thing more or less. Okay. Fewer data points are required for cost function formulation, resulting in a more effective parameter identification. Also availability of accuracy matrices is there, so such as coherence function. We will see what is this coherence function in a moment, and also normalized error function. So there are two parameters which kind of indicate of, which are sort of giving you numerical indication of what is the level of accuracy of the identified model. So we can quantify how accurate our models are, okay, by using this coherence function and normalized error functions. Okay, so this frequency response estimates. Okay, so what we do here is we define this function. Okay, so h j omega relates the input and the output. So in this y, so this entire thing is actually in your sort of what is called this. I forgot the term, Laplace domain. Okay, yeah. So so input is your u j omega. Okay. So whatever input the pilot is giving, that is over here, okay, and output is yj omega. Okay. So this we have measured. Okay, we know what input we are supposed to give, and this is output what we are supposed to measure. Okay, and hj omega is what is going to relate these two things. Okay, this is what we are going to identify, or which is what we want to know. the relation between the input and the output. So these are the corresponding Fourier transforms of the output and the input signals yt and ut. So that is what is given here, and the frequency response function, this is a Fourier transform of the impulse response function h tau. Okay. So that is given by this. See, normally, okay, if we want to look at the response of any system to a transient input, okay, because the input which we are giving is actually a transient input, okay, even though we are giving cyclic input continuously, but it is changing with times throughout. So normally when we want to find a transient response to a transient input, we always resort to the response to this impulse function response, and we make use of what is called Duhamel's integral, or what is the other name for that? Okay, I forgot. Have you heard of this Duhamel's integral? It is, I mean, it is sort of superposition only. Okay, so in what is the other name for? I forgot the name. Okay, I am really bad with names. Other than calling it Duhamel integral, we also call it. It is there in all. I mean, your vibration kind of things. I mean, like. Right, convolution integral, exactly. So Duhamel integral is also called convolution integral. Okay, exactly. I was forgetting the name convolution integral. So if I want to find out the response of a system, okay, to continuous inputs, what we do is that we relate the response of the system to your impulse input, and then we make use of this Duhamel or convolution integral to get that. So the similar kind of thing is being done over here. Okay. So this complex frequency response function h j omega also relates input auto spectral density function, okay, GUU to input output cross spectral density function GUY. Okay. So this we are defining now this spectral density function GUU, which is for the input, and GUY is for the output, and this guy also relates these two things together. Okay, and the definition in terms of corresponding Fourier transform is given over here. Okay, we are not going to go in the mathematics of all this. So based on all this information, we can see that the frequency response function can be determined from spectral functions by using this relationship. So h j omega, from here you can see you will be actually GUY j omega by GUU j omega. So this is input output cross spectral function GUY, and GUU is the input auto spectral density function. So once we have this, okay, and we have the information for GUY and GUU, we can also define something called coherence function. Okay. So this coherence function, which is defined mathematically like this, that is mod of, so it's denoted by gamma uy. Okay, this is actually equal to mod of GUY squared by GUU and GUY. Okay. What this is actually, it indicates how much an output y is linearly correlated with a particular input u as a function of the frequency. Okay. So this is basically measure of this particular thing. Okay. So availability of accuracy matrices, which improves the reliability of the model and indicates the effectiveness of identifying the parameters through a numeric metric, are basically this coherence function. So like we mentioned, that there are numerical matrices which you can use to actually quantify how accurate your model identification is. So one parameter is this coherence function. Okay. This should be always less than or equal to 1. Okay. If it is higher than or equal to 1, then we cannot trust that data actually anymore. Okay. So we have to then carry out something else. Other is your normalized error function, which is defined in this form, and it is dependent on your coherence function itself. Okay. So the expected normalized error in frequency response magnitude and phase can be represented in the terms of the estimated coherence function given like this, where ND is the number of sequences used in the estimation of the spectral functions, and the error in the phase is given by this. So these are the two indices which I can use. And when you start looking at the software cipher, it actually kind of gives you the indication that what are the typical values to expect for these. So what are the range of values when you can say that yes, I mean my model has been identified accurately, and when you don't trust that, and then you have to discard the data, do more experiments, and so on. So sometimes, I mean, you may get the data and you will see that the coherence, okay, function for that actually is not coming out to be nice, because there is too much of noise, or the bandwidth of the input that the pilot was supposed to give, he could not give that bandwidth of input. So based on all those things, then you have to actually either change your requirement that okay, I will identify only a smaller or a narrow model which will be valid only over a narrow range, or then go for more flight tests. Okay. So those are the things. The vehicle equation of motion characterized from the vehicle dynamics are linearized and simplified. Okay, so we already know. Okay, so finally we want to express our equation in this kind of form, and you saw how we get this equation from our original nonlinear flight dynamics model. The finalized parameterized model structure is only established after completion of successful identification, which involves an iterative process. So iterative because I mean initial value of the parameters have to be provided, okay, as a guess, and then the whole process will be repeated over multiple times, and finally you come up with the solution. So what we thought is that, okay, instead of actually going through all this mathematics ourselves and developing our own software from scratch, it is better to use the existing tool. Okay, so we have not really done any kind of exhaustive development of our own tool, okay, for this purpose. But yes, I mean flight dynamics model, we already have our own model and so on. Okay. So the unknown model parameters are identified through an optimization process in which frequency response fitting error is minimized. So every time we are trying to fit, so basically when we are doing in frequency domain, the good part is that we can actually do superposition. Okay. So response for every individual frequency I can add them, okay, and there may be some kind of scaling factor, okay, corresponding to each of these frequency responses, and if I tune these scaling parameters correctly, okay, I would be able to match the response reasonably well, and that is what actually is tried, and we try to minimize this error. Okay. So optimization process is used to minimize the fitting error to ensure that I mean your model, identified model, matches best with the actual flight test data, and this is the kind of cost function which can be used to minimize this error. So this measures how well the frequency response are calculated from parameterized model fit for the estimated frequency, and it's built somewhat like this. The parameter theta is identified through minimizing the cost function j theta. Okay, so this theta is the sort of some kind of weightage factor or something which is actually identified by minimizing this particular function. This is overall architecture of this software cipher, okay, which we are using for this identification, and it offers you several modules which carry out different purpose, or they serve different purpose rather. Okay. So one is frequency response identification called PID, multi-input conditioning toolbox, window combination called composite, derivative identification called derivid, state space verification called verify, and then this frequency response fitting, that is called nav fit, and various modules, okay, they talk among each other and so on. Okay. So it's not very important, it is kind of explains, I mean when you start using cipher, okay, then you actually have to understand this better. Okay. Now coming to the flight experiment and data collection. Okay. So how do we go about collecting the data and carry out the flight test? Okay. So this is a sample, okay, pilot input given to collect data for system identification. Okay. So sufficient excitation is needed to give the test vehicle. So the idea is that we should excite the vehicle in a way that I mean I can get response for all the frequencies which are representative of the model. Okay. So we must give inputs in a way that my helicopter responds to all frequencies, and that is why the pilot, he starts with a low frequency. So he will start moving the stick slowly, and then at some point he is giving actually very high input. This is just pilot input, you can see, okay, which is recorded. So this is a typical frequency sweep input, and you can see that the frequency is actually increased continuously, okay, and then probably it will be decreased again. Okay. So what kind of frequencies do we have to give? So frequency range of interest is a critical aspect before going to the flight test, because you must know, okay, what range of frequencies I need to identify, okay, and what is it that I am interested in. Okay. Is it enough for me to identify frequency of the range of just say the 0 to 10 radians per second, or I need to identify frequencies beyond that and so on. So for validation of simulation models, okay, omega min is 0.3 radians per second. So if you recall, I gave you an example of one of the most aggressive maneuvers for Black Hawk helicopter, and we found that the maximum omega for that kind of scenario was actually of the order of this 0.2 something only, okay, or 0.3 radians per second, okay, fairly small. So this kind of thing is enough for validation of model, okay, but then typically you end up giving 0.3 to 12 radians per second. Okay. So, if you have within this range, then it will kind of take care of all kinds of things, even for smaller helicopters, which are probably capable of much higher rates than bigger helicopters. Okay. For flight control design, okay, we typically want from 1 to 20 radians per second, and typical pilot input, okay, for these things is actually 0.1 to 10 radians per second. For handling quality specifications, we typically give input from the range of 0.5 to 15 radians per second. So, depending on the application, you can choose one of the range, but you can see that these two are kind of fairly, actually this is fairly inclusive except for the lower ranges. Okay. So, the lower ranges are actually more important because they kind of are representative of the dynamics of the blade itself. Okay. So, when you are interested in also validating the blade dynamics, then you have to go for slightly lower frequencies. So, what is the recording length? Okay. So, if I have to go and do the flight, okay, how long should I be flying the helicopter? Okay. How much of data I have to collect? So, some information about that. So, depending on what omega min you are trying to measure, okay, 2 pi t by Td will actually give you that. So, record length, that is at least twice the period of the lowest desired frequency. Okay. So, the time duration for my flight test would actually be automatically come from this. So, if my omega min is say 0.3, so it will be 4 pi by 0.3. So, it will be 40 pi by 3. Okay. So, if roughly 11 pi or something. So, that duration in seconds or in time period you have to collect the data for. Okay. So, for our case, for the small helicopter, we typically did flight tests of 100-second duration, okay, and we collected data for 3 set of flight tests. So, same kind of test we will try to do. So, if I want to excite the mode in longitudinal direction, so I will give the longitudinal input, I will do this experiment and collect data for 100 seconds, and I will repeat this experiment 3 times. So, for every axis I will do actually 3 times each. Some more guidelines. Okay. So, maintaining the operation within the range of linear dynamics is important. Okay. Your input should not be so large. Okay. So, my amplitude of the input should not be so large that the behavior becomes nonlinear. Okay. So, I have to still give input in the small range. So, my perturbation should be very small, the pilot stick movement should be very, very small. Okay. We have to minimize correlation among inputs. So, there should not be a coupling between my input in one axis and the other axis. Okay. So, I should avoid giving input in 2 axes simultaneously, okay, or something like that. Okay. Minimize amount of feedback. Okay. I should not try to correct the helicopter behavior, okay, based on how it is flying. Okay. So, that is the one major challenge, because when you are flying and giving these inputs, my helicopter will start moving all over the place, then it becomes very challenging actually. And we have to remember that the quality of flight data is proportional to the coherence function. So, we have to keep checking, okay, what is the coherence function, okay, for the data before we start with anything else. And the cause for low coherence could be insufficient excitation, like I said earlier. The pilot may not be able to excite all the modes which we desired. Noisy measurement, one very common reason is noisy measurement. My measurement would be contaminated with all the noise, vibration noise coming from the rotor. Output not influenced by the input. Okay. Sometimes my noise, my input and the output which I am trying to look at, there is no correlation in that actually. Okay. I am trying to excite something which the input I am giving for that actually will not have any bearing on that output. Okay. So, that could also be a reason for that. So, this is our model helicopter. We took this off the shelf helicopter T-Rex 450, okay, small scale helicopter. Its rotor diameter, its length is 0.7 meters, height is 0.25 meter, main rotor diameter is around 0.8 meter. Okay. Tail rotor diameter is 0.17 and other details are there. Okay. It roughly weighs with the instrumentation and everything, and battery it weighs around 1 kg. Okay. So, it is a small 1 kg helicopter. So, you can see our goal is to go 1 kg, do 10 kg, then directly go to several thousand kgs, because we do not have any other helicopter in the middle available. Okay. Maximum rotor speed for this is actually around 2800 rpm. Okay. So, this is the vehicle which we chose. The instrumentation which is done. So, on board we have this PX4 autopilot board. Okay. Now, yesterday that is what happened actually, one of these boards got reset in the middle of the flight. So, as a consequence, I mean, just pilot just lost complete control, okay, and it just crashed. So, this normally this is very reliable sensor, we have been using it for quite some time, but last time when we had the accident, we were actually using a Chinese version of this. So, it was actually a pirated version of this particular autopilot board. Okay. So, we thought, okay, it is because of that, but yesterday actually it happened, first time we actually had a failure with original Pixoc board. Okay. but it is an old board, so maybe that is the reason why it actually failed or something. Okay. So this autopilot board actually has 9 degrees of freedom IMU, 3 accelerometers, 3 gyros and 3 magnetometers. Beyond that, it also has a pressure sensor to give you height and so on, and we normally use our own algorithm, okay, which we call NAVIC, okay, to control the helicopter. Okay. So it has various modes available which are typically not available with Pixhawk autopilot. Okay. So Pixhawk autopilot is mainly meant for quad rotors, fixed wing airplanes and some other configurations. It does not give you autopilot for helicopter. So we have developed our own autopilot and so on. Okay. Then we use the roving networks Wi-Fi radio module, wireless LAN access device for ground station communication. Now this helicopter is actually not flown outdoors. Okay. We do this system ID because we are doing only for hovering flight. Okay. So we are doing this indoors using our motion capture system. Are you familiar with this thing? What is this motion capture system? I mean, I hope some of you would have seen videos of quad rotors playing music, okay, playing badminton and whatnot, okay, doing all kinds of crazy tricks on YouTube. Have you seen any quad rotor videos on YouTube where quad rotor is doing something outrageous which you normally do not expect it to do? No? Okay, you should go and check out. Okay, you guys are missing all the fun on YouTube actually. Okay. So there are some very nice videos of quad rotors doing all kinds of things. I mean, coming together, playing actually catch ball. Okay, so one quad rotor is throwing the ball, other is actually catching the ball. Okay. So all those things are actually done in this motion capture environment. Okay. So the key challenge with all helicopters and flight vehicles is normally doing the localization, okay, which is a big topic in your electrical engineering also. Okay, doing localization, especially in GPS denied environment. Okay, when GPS is not working, how do you localize your vehicle and its location and everything else? So to get that, in the indoor environment, there is a company called Vicon. There are now other companies also which manufacture this camera system. So you will have multiple cameras installed on the roof of your room, and these cameras, these are actually IR cameras. Okay, so they throw some kind of IR beam and they look at only IR. And on the vehicle, so if you go back and look at the helicopter, you will see, I don't know if you can notice, there are some small, here there is a marker, gray marker. Can you see that? Yeah, so this gray marker actually is something which reflects that IR light thrown by that camera and projector system. Okay. So in the software, you actually get to see this. So we put 3, 4 or multiple of these markers on our vehicle. So now whichever way this vehicle moves, my camera system will be actually able to track that. So we have the software for this Vicon. It comes with the software on the computer. So on the computer you will actually, so this is showing the camera orientation, okay, for our system. Okay. So we have 8 cameras and that is how they are arranged actually. And so when you go today in the helicopter lab, you will actually get to see these also. Okay. So this system, actually we bought the cheapest version of the system. Okay. Even then it costs 35 lakhs. Okay. Now we intend to buy the more expensive ones, okay, upgrade our cameras, because these cameras have low resolution. So we have a limitation, they cannot work in daylight time actually. Okay. So we have to do our experiments mostly in the evening or night, okay, when the daylight is not there. So this actually, what it does actually is it does triangulation and it actually tracks the motion of the rigid body completely. So it will give you the information about the orientation of the vehicle as well as the what is called the position. Okay. So position and velocity information is also available to you through this particular system. Okay, so these are the inputs which we give. We give lateral, longitudinal and pedal inputs, okay, and collective inputs. And output is typically translational velocity, your angular velocity in form of PQR, attitude of the vehicle, Euler angles and accelerations. Okay. To get the orientation, right now we are using actually quaternion. So instead of using the Euler angles, we make use of quaternions. Okay. So we transfer, so orientation of the vehicle from one attitude to another is actually done using quaternions. In the Vicon, okay. Onboard available, so onboard we have roll pitch yaw and everything, but when we do the system identification, we do not use the onboard sensor data. We use completely the data which is given by the Vicon system. So at one point we actually even did this checking. We acquired the data on board and we compared the roll pitch yaw motion and all those motions from the Vicon and this, and we got a exact one-to-one matching. Okay. So we know that yes, it is correct. So here is a sample flight video of acquiring of this data. Okay. It may get a bit scary at some point. So, main challenge comes with the heave motion. Okay. So, other motions are fine more or less for hover, but the moment we want to do the heave dynamics, okay, we start giving up and down motion, and you know the down motion for helicopter is very bad, okay, because of the vortex ring state. So, you will see in this point, I mean at one point it will actually go and hit the ground also. See, now it is giving very high frequency, okay, very small inputs, but very high frequency. Okay. Now, you are only giving that input, okay, so it will start losing thrust and it will start actually coming down also. So, you have to be aware of that. Normally, for big helicopters, these kind of experiments are done at much higher altitude. So, you do not have to worry about, I mean, helicopter coming and hitting the ground. So, this is a combination of some other. So, this is now giving pitch input. Okay. So, you can see the continuously pitching motion is being given. Okay. It's very noisy, sorry. I was thinking that why the sound is not coming for the rotor, because helicopter makes a lot of noise. This is the yaw motion. This is very challenging actually. This yaw thing is very challenging, okay. Because even for the pilot, I mean, he starts losing the bearing, okay, of the vehicle, okay, when he leaves that, and it is very fast, very fast dynamics. Very sensitive, very sensitive. It starts spinning also. No, it ends up spinning actually. This is heave dynamics. Yeah, in this I think it will come down and hit the ground at one point, because now you have to give, okay, make it move up and down at very fast rate. Up is fine, but the going down is very challenging, because I mean small input you give and the thrust is offset, it will start falling like a stone. Thought you should hear to some sounds also. I think that is it. Yeah, that's all. Okay. So it was combination of various, okay, flight test cases which we flew to acquire the data for the entire thing. Okay. So here are some of the sample inputs, okay, which were given. These are actual inputs from our experiments, okay, what were given. So you can see this. Okay, this is first one is actually lateral cyclic. Okay. So it gives in batches. Okay. So you increase the frequency. See here you can see the frequency is very fast. Okay. So you start with very low frequency, start increasing it slowly, and same kind of thing is over here. Then this is longitudinal. Okay. Lateral actually is fine, but longitudinal what happens? I mean, if you start giving big inputs, it actually starts oscillating very fast. Okay. Then the pedal input, okay, and collective. Okay. Or maybe this is actually just for the one axis. Okay. This is actually only for lateral. That's why I mean this main input is in this direction, but you see inadvertently you are actually giving some input in the other axis also. But I mean it is okay. It's not that high. Okay. The main input is actually in this lateral direction only. So this is for just the lateral sweep actually. Yeah. And corresponding to that input, okay, this is what the output you end up getting. Okay. So measurements you can see here are. This is delta, this is the lateral angle, okay, this is the rate, this is phi, and the one lateral acceleration, and this is my lateral velocity. So, all this information is coming from my Vicon system. So, normally when we do control of these vehicles using Vicon, what we do is that actually the position data for the vehicle is actually sent from the ground control system. So, we have a computer which is actually getting the data from the Vicon, and we communicate that information to the helicopter. Okay. So, wirelessly. Okay, so, this is on axis records collected during a lateral frequency sweep experiment. Okay, so, this is what we have. So, these are the responses which we did for that particular axis only. Okay. There will be data also for corresponding to the other axis, and this other axis information is also important because of the cross coupling nature of the helicopter. Now, what are the challenges? Excitation of vehicle in confined space. Okay. So, when you will see our helicopter lab is pretty big, but then our camera system is only there in the small area in the whole thing. Okay. Because the camera has its own range, you cannot actually put them very far apart, then it will not be able to see, and there will not be enough overlap for you to track the marker accurately. Sudden loss in altitude during the heave sweep, this is biggest challenge. Okay. Because the moment you give a downward input, okay, you cannot give a downward input fast. A small input itself will start making it fall down, okay, because of the gravity. So, that is the biggest challenge, okay, how to get the heave data, okay, for us. Obtaining good data for yaw also was quite challenging, because I told you earlier yaw sensitivity is very, very high. Okay. Small imbalance, it will make it spin immediately. Okay. And it is also difficult to give low frequency excitation, okay, because low frequency means, I mean, you are giving slow input. So, the helicopter has actually more time to react to that slow input. So, I am giving change in theta 1s. By the time I bring it back, my helicopter will start moving forward. Okay. It will acquire some forward speed already. So, this another challenge is to give this low frequency input. High frequency is fine, I mean, I can keep oscillating very, very fast, and helicopter will more or less maintain the same position. But low frequency, I mean, the confined space comes into picture, okay, because then it will go outside the range of the camera, okay, or it will go and hit the wall. So, those challenges are there. So, now once we move to outdoor, so our plan is to now see, this was done for the small helicopter indoors. Now, we have instrumented a helicopter using RTK GPS. So, RTK GPS is effectively almost same as the accuracy of this Vicon. So, Vicon can give you accuracy over millimeter level, centimeter level. Okay. Actually, with a higher resolution camera, you can even get probably 5 millimeter, 4 millimeter kind of accuracy, or even smaller actually, okay, depending on the area you are looking at. So, even with RTK GPS, you get centimeter level accuracy. Normally, GPS actually data is corrupted on purpose, and you end up with accuracy of like plus minus 5 meter. So, if you turn on your phone GPS, it will tell you accurately in the vicinity of like 10 meter circle or something like that. But if you use RTK GPS, it is called real time kinematic GPS, it actually detects the error and corrects for that by using a stationary GPS on ground. So, if you use that, then we end up with a much higher accuracy, which gives you almost centimeter level accuracy. So, we are planning for that. We have already put this RTK GPS on our helicopter, and we will call a pilot, and hopefully we will be able to do flight test with that. Okay, a skilled pilot who is used to of doing this 3-dimensional flying for helicopters, and hopefully we will have this difficulty, some of these difficulties removed, because then I mean we will fly in our flight lab where we have a 1 kilometer long runway, and we have enough room hopefully to get all the data which we want. Okay. So, this is some example frequency response, okay, from the non-parametric model. So, in this case we are just doing rigid body model fitting sort of. Okay. So, we are not bothered about, I mean, any physical model inside that. So, this is for input is lateral and output is your corresponding roll rate. Similarly, this is the input is lateral and output is your velocity in the y axis. So, we did not actually focus so much on this non-parametric model identification, okay, because that is not of our main focus. We want to be able to do a more accurate parameter estimation based on the physical model. So, we set up a model structure and we try to fit our model based on that structure. So, let us see what is the model structure which we are looking at. So, these are the same equations which you have already seen, okay, Newton-Euler equation. So, this is always going to be there, okay, it is representative of the rigid body motion of the helicopter. So, I do not have to explain this, you have already seen it several times. You have seen the equation in this form also, okay, this is a simplified rotor dynamics, okay, where we are looking at the roll lateral cyclic and the longitudinal cyclic, sorry, not cyclic inputs, it's rather lateral flap and longitudinal flap angle. So A and B are actually those, beta 1c and beta 1s dots. Okay. So this also you would have seen probably when Nidis derived the simplified linearized model, okay, Kai-Chen-Lee model and so on. So we use this version of rotor dynamics, okay, and we try to identify these parameters, this Kp, Ib, because initially we don't know these. Okay. There are ways to calculate them, okay, using experimental things and using analytical techniques, but then these parameters are the key parameters actually which governs the overall dynamics. So knowing them accurately is very, very important even for the control design point of view. So like we discussed earlier, a 6 degree of freedom rigid body model does not capture the rotorcraft dynamics with complete accuracy or the desired level of accuracy. So we have to bring in other things, because the whole rigid body is actually actuated or excited by the motion of the blade. Okay. So the blade actually gives a feedback which basically results in the motion of the fuselage. So including the rotor dynamics is also very, very important. Okay. And this is the most simple way by which you can include the rotor dynamics. Okay. So this is the hybrid model, okay, which accounts for the simplified rotor dynamics also. So now we are bringing 6 degrees and now we are bringing 2 more degrees, which is basically the 2 corresponding flap angles. Now this all the equations which we saw are non-linear, we know that, okay, we can linearize that. Okay. You have already gone through the linearization process with me. Okay. So just by giving this perturbation, small perturbation thing, we can linearize the whole equation about some general operating point. These are the corresponding rotational equations, we have seen all those things. And we can even do your Taylor series expansion, okay, for delta x, and we can now come up with these stability derivatives xu, xv, xp, x delta lateral, x delta longitudinal. These are actually your control derivatives, these are your stability derivatives. So now we can put all this structure in place and put an equation like this. So this is your equation for the entire 6 degrees of freedom. Okay. So you can see this has actually 1, 2, 3, 4, 5, 6, 7, 8. 8 equations are there. One equation which is missing is u, v, w, p, q, r dot is there, phi, theta, psi is not there. Okay. So psi dot dynamics is not there, like I mentioned. So we are looking at the rates, but we are not looking at the yaw angle thing. Okay. So we dropped that primarily because of this very high sensitivity. Okay. So including that, we are not able to get actually the nice coherence and everything. So we left that out because it's anyway simplified dynamics. Just the yaw alone is very simple. Okay. It's not very difficult to design a controller just to take care of yaw dynamics separately. So that equation is actually dropped. Okay. The equation in psi. Okay, and the corresponding inputs are your lateral, longitudinal, pedal and collective. Okay. And the equation will be populated in some form like this. Now we have to give guess values for all these things. Okay. And that is where the challenge comes, okay, when we try to identify the model using cipher. So this is the general form of the state space model. Okay. Our state vector is this u, v, w, p, q, r, a, b and phi and theta, no psi. And measurement vector includes u, v, w, p, q, and so we can measure the 3 velocities, the 3 angular rates, okay, body rates of course, and your accelerations, okay, in x, y and z. So these are the translational accelerations. Okay. Input vector is lateral, longitudinal, collective and pedal. Pedal is basically your theta collective for tail rotor. Now when you also bring in your parameters corresponding to the flap dynamics, okay, then the bigger equation becomes like this. Okay. So this has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we had earlier 8 equations, now we have 10 equations. Okay. So we have now brought in 2 more equations and 2 more parameters, which basically represents the approximate blade dynamics, okay, simplified blade dynamics. So those are also now part of this. So we did identification for the rigid body alone model also, and we did it for the this coupled 10 degree of freedom model also, okay, or rather 8 degree of freedom model. Okay. So initially we start with simple seesaw identification. We just do identification in single axis, because that kind of gives you some simple information which you can easily see, and yes, okay, things are going on fine. Also helps you learn the software, how to operate it and so on. So, we normally do that first, and we identify key on axis parameters. So, this is longitudinal seesaw dynamics, u dot, q dot, theta dot, okay, just the longitudinal alone. Similarly, lateral is v dot, p dot and phi dot, okay, and you have simplified smaller equations like these, which you can identify easily. And with this is the yaw seesaw, it is even simple, just one equation, and this is the heave seesaw. So, just w dot, w is the vertical velocity and corresponding zw w and collective control, okay, that is all. So, all these models can be identified and the corresponding parameters are given here, okay. The percentage of Kramer-Rao bound, okay, there is Kramer-Rao bound which tells you, okay, again the reliability and accuracy of these things, okay. So, that is given here in percentage, insensitivity is given in percentage. So, all these parameters can be also used to now create small simple transfer functions, okay, which you can use for linear control design and as well. So, here is the validation or the identification result. So, what we have here is magnitude and phase diagrams and the coherence, corresponding coherence. So, remember coherence has to be less than 1. If my coherence is higher than 1, then I cannot trust the data and identification. So, I have to discard some of the data. So, there were times when we use data from a particular flight and we are not getting good coherence. So, if we remove the data for that particular thing, then it works fine, and we have to then get more data if I want to improve the accuracy of estimation and so on. So, this is our pitch seesaw model, okay. Magnitude correlation, okay. So, it is going up to nearly 10 radians per second. So, these simple models, okay, in single axis, okay, you can see for higher frequencies match is relatively okay, at least for the phase. For lower frequencies, you see it has slightly less accuracy, right. At higher frequencies it is reasonably good, and the reason is also again the same thing, that we cannot actually give inputs at this high low frequency values, okay. That is the challenge, which because of the limited space and everything. Okay, this is the pitch, this is the roll, again similar thing, okay. Compared to this has slightly better roll, lower frequency, because roll, I mean I can give smaller inputs and my motion is actually smaller relatively, okay. So, I can give much fast, yeah. So, roll motion is relatively slower also because the drag is higher, okay. In pitch your velocity is typically faster for the same input, because I mean your frontal area is smaller. In the side flying, I mean your projected area is higher, so it will have more drag. So, you can relatively give low frequency inputs somewhat more easily. So, here you can see that this is better actually, so slightly better correlation at the lower frequencies. This is heave seesaw, okay. Heave, I mean we did not do so bad, okay, it was okay, not that bad. Yaw seesaw, okay, is also okay, single axis is fine. And after we have done this identification of each of these models, okay, we have to do the time domain verification, because this is actually just the check of the range of frequencies you are actually able to match. Now, when I use this identified model and use it for a test data which is not used in the identification process, how does it compare? So, here is the comparison, okay. So, this is the input I is given, okay, and this is the V generated, this is the P, and this is the acceleration. It is fairly good. Velocity is slightly off, but you can see P and acceleration data are fairly okay. Similarly, for longitudinal, again it is quite good, Q is slightly off, but still not so bad. Again, this is time domain verification for your yaw. Okay, so R you can see this is not matching so well. Okay, this is the input which was given in pedal. Accelerations are matching okay. This is for the heave actually, collective and heave. It's fine, but for higher frequency it is, or sorry, after some point it is actually giving slight offset, but overall it is capturing the trend reasonably well. So, you can see that single axis identification, and if you are giving a motion in only single axis, okay, your correlation is okay. But what happens is that, I mean when you give the input in a particular axis, you typically end up with a response in the other axis also, okay. That we are right now not even looking at actually, okay. Now, MIMO identification, okay. So, this is the coupled lateral directional mode. So, here I mean U, P and phi are all included, sorry, V, P and phi. Then coupled lateral longitudinal model, B, P, A and Q. So, we again when we go to MIMO also we do not directly go to 6 degree of freedom model directly, we first make it slightly more. So, single degree is very easy to identify because we are only looking at couple of parameters. So, we get that model, then we go to this 3 degree or 4 degree of freedom models, okay. So here again, I mean, we'll identify. So we typically will have knowledge about some of the parameters based on our previous CISO models. So we can use them as guess now, in the overall model. Here is the correlation for that. So you can see phase is pretty bad here at low frequencies for V, P, AY, and so on. This couple. So this was the longitudinal. So no, actually, sorry, both of them are lateral. Okay. No, this would not have been lateral, right? Yeah, this is actually sorry. This label is wrong. This is actually longitudinal. Sorry, lateral. This is lateral. Okay, and this is yaw. Okay, it's fine. Actually, it's fine. Okay, this was just a lateral part, and this is the your directional part. So this is combined lateral directional model. So this has actually lateral things. P, your y acceleration, and your velocity, side velocity, and here you have your yaw velocity, corresponding rate, and your yaw acceleration. This is the result of the identification. So that was the data which was used for that. And again, we are getting reasonably good correlation up to like slightly higher than 10 radians per second. So reasonably good. Now this is the lateral longitudinal model. Okay, so here also correlations are fine except for the slightly lower frequency. And carrying out all this process gives me corresponding parameters. Okay, and the Kramer-Rao bound for all of them. Okay, and their corresponding values. So this is identified lateral yaw model, and this is lateral longitudinal model. So after doing this partial model identifications, now then we finally move to full rigid 6 degree of freedom model identification. Okay. So now we will try to do this collective 8 equation by 8 equation model. Okay. But the degree of freedom is 6 basically. So you have to again select the frequency ranges for each of the inputs. So for lateral we set 0.6 to 20. For AY, so this is lateral and P correlation, this is lateral and your AY correlation, and so on. So these are the various ranges which we have selected, okay, for identification process, and you can see each of these parameters will have different frequency ranges. Okay. When you look at the Cypher manual, Cypher actually through various examples and so on, they actually talk about these typical ranges which you have to use for different parameters. Okay. And with experience, again you have better estimate for these numbers for a particular helicopter model. Okay, because for smaller helicopters it will be slightly different. For bigger models, these range will be slightly different, and so on. So now, okay, we have to be very careful. Okay, this whole thing is iterative in nature. Okay, and we have to keep an eye on frequency error costs and Kramer-Rao percentage. Okay. And finally carry out the time domain verification. So this is the result for the identification for 6 degree of freedom. Okay. Here we have V, P, and AY, magnitude, phase, and coherence. Coherence is fine here, it is going close to 1, but it somehow remains below 1. Now this for U, Q, and AX, again it is reasonably good. Consistently we get this sometimes offset or error rather. Okay, at low frequency for Q, which is longitudinal. For yaw, it is looking fine here. And this is for your W and your AZ. So now I mean all the individual components for the same set of flight tests. Okay. So earlier we had all these individual components for different flight tests where we were only exciting certain particular axes. And this is the identified result, okay, for various parameters and the corresponding cost functions. Okay, this was actually just the cost function, okay, of how much of minimization you could achieve for different parameter, and this is the result finally for your stability matrix, and this is your control matrix. Then we proceed to 8 degree of freedom model identification. So same, now this whole equation is used, and we go through same things. We first set the frequency range for each of the axis parameters. Then we look at individual components, translational, longitudinal, lateral dynamics. We try to decouple that. Okay. So here XU and YV are key parameters. For heave dynamics, we have ZW and Z collective as key parameters. For yaw dynamics, we have NR and N pedal. For coupled roll and pitch equations, we have the rotor time constant, which is very, very important. Okay. This time constant is same as the delay of the phase angle which we are talking about. Okay, that 80 degrees phase angle and 90 degrees phase angle which we were talking in when we looked at the your rotor equation of motion. This is the same time constant. So we are now using this approach, we can actually identify this, and this is something which has the most significant influence on the response of the helicopter. Then flapping spring derivatives MA and LB, and the entire state space model. Okay. So these are the again the tables of identified parameters for this small helicopter. Okay. Cost function values, and these are the results for identification: V, P, Q, AY, U, P, Q, and AX, and V, R, and AY. So these are again, I mean, all the frequency domain data, I mean, results actually, because I mean we are looking at magnitude and phase. Then finally at the end we do the time domain verification. Okay, because this is the key thing. This is where you want to see whether your whatever you have identified, okay, matches well or not with the flight test data. So you can see the dashed lines is actually your model, and solid lines are your identified the flight test data. So for the input lateral, for this U matches okay, not that great, okay, but V and W are matching quite well. So in this, because we are giving lateral cyclic, so our main motion is actually in the lateral direction, but as a consequence there is some small motion in the longitudinal direction also. So you can see lateral velocity V is actually of the order of 1, while this is actually 5 times less than that. So the lateral motion, the lateral input is causing some vertical, your axial longitudinal motion, which is of much smaller magnitude. So that also contributes to the error which we get. Okay. So it is smaller number, and getting that actually accurately will be less challenging. More challenging. Okay. W is matching fine. P, Q, R, they are matching quite well. AX, AY also, and AZ. Okay. So AZ actually is the vertical acceleration. So you can see the flight test data has this lot of high frequency data. Can you tell me what could be the source of this? AZ is my vertical acceleration. It has this oscillation, right? A lot of oscillation is there. Can you tell me what is the source of this oscillation? So this actually is measure of your rotor thrust in the vertical direction. Okay. And this high frequency is basically the oscillation in the force which gets transferred to the fuselage, okay, from the rotor. So that is actually showing up in this somewhat. Okay. Now this is for the, so this was for the lateral input. Now we are doing verification for the longitudinal input. In this case now, because the main axis response is actually your U, so it is matching very, very well. V is not that bad here, okay, because V is somehow also large here in this case. W is actually showing some strange offset here. P, Q, P is slightly not that great here. R is also not so good here, but overall they are not bad. I mean, if you see the overall trend of the motion of the helicopter is actually very well captured. Okay, it is not going to match at every point, okay, and tell you exactly the exact value, but in general I can say it is quite satisfactory. So this was actually for the pitch doublet. So when we do verification, we give these doublet inputs, that is up, down again. Okay, so that is a doublet input. This is yaw doublet. Okay, so here also we have given doublet input in yaw. Yaw is still slightly tricky to match, but if you see U, V, W is fine. P is also okay. Q and R are good here. AX is again showing this strange bump over here in the flight test data, while the model is actually smooth. And AY and AZ are also somewhat okay. So overall we see that, I mean, it gives reasonably good correlation. This is actually the heave doublet. Okay, UVW is looking good. P has this strange doublet kind of thing. This is probably due to some inadvertent input by pilot. Okay, so he is trying to mainly give the input in the collective, but this motion suggests that maybe the pilot ended up giving some small input in cyclic also. Okay, and which resulted in this small peak in the flight test data. So again, this is also satisfactory. So that is probably all. Okay, so that is fine. Okay, so now I will stop here basically. So this is the validation of the results. So this is how we go about doing the entire thing. We have done this now for hover only so far. Now our intention is to, in coming months, instrument our bigger helicopter and carry out this entire process for the bigger helicopter with RTK GPS and so on, and do this identification for hover as well as for other flight conditions. Okay, so some moderate speeds like advance ratio, or I mean in this case advance ratio is not very meaningful. So speeds like say 5 meter per second, 10 meter per second, 20 meter per second, probably 15 and 20. Okay, so we will see how many points we can do, because doing at higher speeds also may be challenging, because I mean if you are going at a very high speed, I mean 1 kilometer may not be enough for you, okay, to maneuver the vehicle and give all the inputs at that speed. Okay. So we have to see all that. Okay, so that's all. I'll stop here. Any questions?